They say it's all the journey, not just the destination. And in trigonometry, well, that's just our information. You have steps, you have a process that depends all along the function. It's important that you know what it could be. You've got sine x and cos x, different origins and x-intercepts, but they have the same base y values and range. -1, 0, and 1. From 0 to 2 pi, you've got one cycle separated by 4 equal parts between, where the x value gives an exact number mentioned before. By using this key knowledge, any cos function can change to sine, or vice versa with simple adding or subtracting, also known as a horizontal translation. Let's look at an example here. Cos to sine, we'll subtract to under pi to make the graph shift over to the right, or adding to the left if you're doing sine to cos. These are trig rules. They're gonna help you the most. Dance break, because too much math might make your brain explode. Whoa, yeah. But what happens when something doesn't fit? In our predetermined outlines from before, it's here that we'll meet the special triangles and the angles that'll make the insides whole. In a triangle, the angles add to 180 degrees, and we are knowing that's half of 360, full circle. And since a full cycle equals 2 pi, we should know that the angles add to regular old pi. So 30, 60, 90 degrees becomes pi over 6 over 3 and 2 if you please, with the same side lengths of 1, 2, and root 3. And a similar state goes for that 45 degrees with now pi over 4, pi over 2, and the side lengths of 1, 1, root 2. And using these two triangles, we can get the exact value of, well, pretty much any trig ratio. Say you need to find sine of pi over 12. Well, that doesn't fit in anywhere that we know of. But by separating this up into smaller bits, you can easily find something that fits. Let's go. Multiply by 2 and get 2 pi over 24. Now, what two numbers have we seen that multiply to 24? Well, 4 and 6, those we know, so simply put that pi above and below, cross multiply to get the same denominator, and arrange with signs until it equals 2. And if 6 minus 4 equals 2, then pi over 4 minus pi over 6 is going to give us pi over 12. So then you take the sine of each angle, which is opposite over hypotenuse, and that would equal 1 over root 2 minus 1 over regular 2. And since we need a common base, we're going to cross multiply again, and that's going to end us with a 2 minus root 2 over 2 times root 2. It's going to give us an exact value. Let's kick it up a notch. Let's say you have a graph, and it doesn't fit the basics of anything that we have. But look a little closer, and you'll see that's a lie. It's just another equation for you to recognize. Let's use sine, because I find it's easier to rhyme. And look all at the numbers that we usually just never mind. Expanded fully, it's 1 times sine of 1 x minus 0, and add on another 0 at the end. Now, why does this matter, you might inquire? It's because these numbers set the base for all of the ladders. Substitute the numbers for some variables, and you'll get an equation that everyone should know. A times sine or cos or tan of k times x minus t. Follow that up by adding c. Each letter represents something that you'll see. A, the amplitude, also called a vertical stretch or compression. For this, we'll use the min and max points as -2, -8. Subtract the min from the max and divide that value by 2. That's the distance to the midline, also called the amplitude. K, the period, or how many cycles are in 2 pi. Looking here that we see that our graph completes 2 times. That means our K value is 2. And to find our period, that's 2 pi over K. That means the period is pi Oh yeah, D. The horizontal shift left is add and right subtract. And you can see here that we're close to pi over 2, but not quite. It's about halfway. And half of pi over 2 is pi over 4. That means our D value is, you guessed it, pi over 4. C. The midline. It's quite important. It also uses max and min, just like our amp. But you're gonna add these values together. Instead of subtracting, divide by 2, and that's your C. That's a GG. The last thing to know is the trig identities. They'll make your math life from here now on easy peas, but there's a lot to go through. So let's try to do it quickly. Grab a paper and a pencil and take some notes, please. Reciprocal functions are a bit of a mouthful. Cosecant, secant, and cotangent are gonna be stuck in your skull. That's sine, cos, and tan, all under a value of 1. But we're just at the beginning. Let's have some fun. Pythagorean identities, well, they use squares and 1, since with any exponent, it doesn't care. Sine squared and cos squared, that gives us our 1, and we can rearrange that for any sum. Compound angles is where it gets complicated. That's when you have 2 variables inside. Addition or subtraction, it doesn't matter. We can demonstrate this with x and y. For sine and cos, it uses both, while tangent keeps to itself. The same goes for our double angles, which uses 2 times the angle up on the shelf. Yeah. But how can we know that these correlate? Well, if we replace both here with an x, we can see the compound angle proves the double angle. I'll show you here, right up next. Let's take cos here and make it into x plus x, then expand to the full compound. And you can see here that anything times itself is a square, so that gets us cos squared minus sine squared. Right? Does that look familiar? Well, it should. That's the same as our cos of 2x. Any problem from now on should be easy. You agree with me, right? Trigonometry is no longer a hex. Yeah, you know trig now. Remember to practice, or else you're gonna forget everything. That would be really bad. That'd be really bad. That'd be pretty bad.